I might have mentioned before how electric and magnetic fields are really one and the same, and that light is a self-propagating electromagnetic wave. So cool. So how do we actually know that? And can we solve some stuff to get some information about that? Yeah, we can. So we are going to do a little bit of manipulation on Maxwell's equations to get the velocity of a wave that would be self-propagating. Okay, so what we're going to do is use a little math trick where we have del cross some vector A, which is going to simplify to, oh my gosh, del cross del dot A minus del squared A. Oh, what's that? Okay, so we are going to do that to equation 3 and equation 4. Okay, and I hope that I have enough space here. I'm going to erase the force equation. So first we're going to do number 3. Okay, so del cross E. I tried to do a vector sign and the closed bracket at the same time. Didn't quite work. Okay, so that equals del dot E. Oh, I forgot to mention. Okay, so where does light travel? In a vacuum. Well, I guess through everything. But we are going to ask what happens when we have electric and magnetic fields in a vacuum, aka when rho equals 0 and when j equals 0. This is a critical piece of the equation. Okay, so minus del squared E. Okay, and since we apply this to one side of the equation, we have to apply it to the other. For simplicity's sake, we're going to go back to the original form of the equations. Equals this plus that. But do keep in mind that this is going to go to 0 since there's no charges. So then we do, on the other side, we do del cross negative dv dt. And then we can bring this in, so we're going to get negative d dt del cross b. And we want to get rid of all of the magnetic field terms, and so we're going to replace it with this equation. This is 0. And so what we're going to get is negative d dt of mu naught epsilon naught dE dt. And this simplifies to negative mu naught epsilon naught d squared E dt. And so now we have these two pieces equal this piece. This is 0. And so we end up with negative del squared E, oopsies, that's a vector sign, not a square, equals this. And so the negatives cancel. Boom. Okay, so that's equation number 1. Whew. And we're going to do the same thing to del cross B. So del cross B equals our little math equation, del of del dot B. Oh, that's easy peasy. That one goes to 0 also. I love when that happens. Okay, minus del squared B. And then again, we're going to do the same thing. We're going to do del cross the right side of the equation, del cross mu naught epsilon naught dE dt equals mu naught epsilon naught d dt del cross E. And again, we want to get rid of all of the E terms and just get it in terms of the magnetic field. So we're going to replace it with this negative rate of change of the magnetic field. So we end up with mu naught epsilon naught. It's a negative, so we toss the negative out. D dt of dB dt. Hey, okay, this is cool. We're getting there. Negative mu naught epsilon naught d squared b dt squared. Okay, and then we get these two pieces equal to each other. So, whew, all right, we're going to move all of that over here. Del squared b, this piece, there's a negative there, equals negative mu naught epsilon naught d squared b dt squared. Boom, and the negatives cancel again. Whew, okay, not too bad, not too bad. Hang in there with me. Okay, we're gonna get rid of a lot of this other stuff and just focus on these two. Boom. Wow. Okay. So from classical from wave from wave stuff, wow, my brain is fried. From basically like the 3D let me look at my notes because I totally just spaced. The 3D wave equation is what it's called officially. Is this del squared f, where f is some general function, equals 1 over v, v squared, the velocity of the wave, times second partial derivative of our function with respect to time. Hey, that's like the same thing, right? Look at that. How convenient that other people have done all this work for us. And so this is why people are like, why does pure math matter? Well, because people come up with these things and then you're like, hey, look at that, I can apply it. It also, some people also love the fact that pure math just exists, and that's fair. It doesn't need an application, but it also can be useful. The two are not mutually exclusive. Okay, so, getting ahead of myself here. We will notice that this term, 1 over v squared, hey, what's up with that? That's basically, both of those are well, constants, I guess. These are in this case. And so we can solve for the velocity of this wave by setting 1 over v squared equal to mu naught epsilon naught. And we solve for v, and we get square root of 1 over mu naught epsilon naught. These are constants. If you look them up and you put them in this equation, you will get 299,863 380. Did I just do that right? 0.47 meters per second. Meters per second. AKA 3 times 10 to the 8th meters per second. Whoa! So cool. So that is the velocity of light. And now we're like, yeah, of course it is. But I want to blame Maxwell for this, or give credit to Maxwell, however you put it. Can't totally remember, but when this was first discovered, it blew folks' minds. They were like, wait a second, light is an electromagnetic wave? Just like that. Yeah, this revolutionized things. And it came out of these equations from classical electrodynamics. Look at that. So cool. Ha, okay. All right, so I'm going to leave it there for now. I hope that this was helpful in your study of physics. Please let me know if there are other topics in electrodynamics that you would like me to cover in the future. Can't promise how quick I will get to them, but I will add them to the list. All right, thank you so much for watching, and we'll see you next time, friends. Bye!